film opens in silence. The black of space stretches infinitely, broken only by the soft shimmer of distant galaxies. Like frozen embers in an endless sea, a slow voice emerges. In the grand theatre of existence, we are but a flicker in the cosmic dark. And yet, around us, the universe breathes with secrets far beyond imagination. From the quiet birth of time to the whispering edge of black holes, everything seems to follow laws. Precise, elegant, divine. But then, something doesn't fit. Something vast, unseen, and relentless lurks in the cosmic background. It bends galaxies, pulls the fabric of space-time, and accelerates the universe itself. This is the greatest enigma of all. The mystery of existence itself. What is the universe made of? Why is it expanding faster than it should? What lies beyond the horizon of what we can see? Through the eyes of humanity, from ancient astronomers to modern physicists, this is a journey into the unknown heart of creation. To confront the question that has haunted science for a century. What is the universe hiding from us? For most of human history, the night sky was a cathedral of stillness, eternal, unchanging, and absolute. The stars, ancient watchers, seemed fixed against a dark and infinite canvas. The heavens appeared perfect, harmonious, and divine, a silent clockwork that had always been and would always be. But in the early decades of the 20th century, that illusion began to tremble. A faint ripple of truth was about to shatter the oldest belief humanity had ever held, that the universe itself was timeless. It began atop Mount Wilson, in the chill air of California's San Gabriel Mountains. There, under the vast dome of the Hooker telescope, the most powerful eye ever built at the time, a quiet man named Edwin Hubble gazed into the deep dark. Through that telescope's glass, the universe itself was revealing its secret motion. Hubble had been measuring the faint light from distant smudges once thought to be small clouds of stars, nebulae within our own galaxy. But his observations told a different story. These were not mere clouds. They were vast island universes, galaxies, each containing billions of suns. The cosmos was not the small, enclosed sphere humanity had imagined. It was an endless ocean of galaxies drifting through the void. And when Hubble compared their light, he noticed something astonishing. The spectral fingerprints, the lines of light emitted by these galaxies, were stretched, shifted toward the red. The farther a galaxy was, the greater the shift. It was as though space itself were pulling them away, like debris scattered from an unseen explosion. The meaning was clear and devastatingly beautiful. The universe was expanding. This was not merely a discovery of movement. It was a revelation of origin. If galaxies were moving apart today, then at some distant moment in the past, they must have been closer, infinitely close. The universe had once been compressed into something unimaginably small, dense, and hot. From that singular, blinding birth, time and space themselves had erupted outward. The revelation was radical. It transformed cosmology from a study of static stars into the story of a living, evolving cosmos. But not everyone could accept it. One man, perhaps the most brilliant mind of the modern age, resisted this truth: Albert Einstein. Before Hubble's discovery, Einstein's equations of general relativity already suggested a troubling possibility. The mathematics implied that the fabric of space-time should not be motionless, that it should either expand or contract under the weight of gravity. Yet Einstein could not believe that the universe could be anything but eternal and unchanging. To preserve that ancient idea, he added a strange term to his equations: the cosmological constant, a repulsive force meant to hold the universe still. It was an act of mathematical defiance against the universe itself. But when Hubble's data reached Einstein, the illusion of stillness finally collapsed. Standing in the cold air of Mount Wilson, after peering through Hubble's telescope, Einstein is said to have murmured, "Now I see the universe is expanding." He later called his cosmological constant the greatest blunder of his career. In that moment, the cosmos changed forever. The universe was no longer a static backdrop for creation. It was creation itself, a living story unfolding through time. This realization struck deeply at both science and philosophy. For the first time, humanity had evidence that time had a beginning. The stars were not eternal fires burning in the night. They were the luminous afterglow of an ancient event, the Big Bang. The very phrase would come later, coined in jest by astronomer Fred Hoyle, who refused to believe it. To Hoyle, the idea that all matter and energy had burst forth from a single point of nothingness was absurd. He argued instead for a steady-state universe, one where new matter constantly formed as the cosmos expanded, keeping it eternal. But as the decades passed, evidence mounted against that comforting vision. Every measurement of the cosmic sky, every whisper of starlight, pointed back to a single origin, a singular moment when everything we know came into existence. The birth of the universe was no longer myth or theology. It was physics, and yet this revelation was far from complete. In the early 20th century, telescopes were powerful, but still blind to the faintest whispers of the past. Astronomers could see galaxies, yes, but not the origin of their light. They could not yet glimpse the first moments after time began. So, they turned to theory. If the universe began in a hot, dense state, it must have left behind a residue, a faint afterglow of heat, stretched thin by expansion, filling all of space. It would be cold now, just a few degrees above absolute zero, but still detectable. For decades, it was a silent prediction, a clue waiting to be found. Meanwhile, the emotional shock of an expanding universe rippled through the cultural world. For poets, theologians, and scientists alike, the idea was both terrifying and magnificent. It meant that everything, stars, galaxies, life, was temporary. That creation was not a completed act, but an ongoing process. The philosopher Arthur Eddington once wrote, "The universe is not so much a mechanism as it is a thought." In this era, science and philosophy began to converge, both gazing at the same vast question: why does anything exist at all? Yet as human instruments reached farther, the answers only deepened the mystery. Galaxies were not evenly scattered, but clumped into filaments and clusters, vast cosmic structures stretching across hundreds of millions of light years. Even now, in Hubble's data, faint irregularities whispered that something unseen was shaping them. Something that did not emit light. The visible universe, it seemed, was only the surface of a deeper reality. The pioneers of cosmology pressed onward. They mapped the distances between galaxies, measured the faintness of their light, and found in those numbers a pattern of expansion that matched no simple rhythm. Space was not just expanding, it was accelerating. Though that realization would come decades later, its shadow already hung over the data, waiting to be seen. And beneath it all, a question pulsed quietly, hauntingly. If the universe is expanding, what lies beyond it? No telescope could yet answer. No equation could yet reach that far. The cosmos was growing, but so too was human awareness, an awakening within the very fabric of space-time. In these early years, the language of the universe was being rewritten. Astronomers no longer spoke of celestial spheres or divine order. They spoke instead of curved space-time, redshift, and cosmic evolution, a lexicon of infinity. But behind their words, something more fragile lingered: awe. For as they looked deeper into the cosmos, they began to see themselves reflected back. Every galaxy, every distant light, told the same ancient story. A universe that began as a single blinding point of creation and has been unfolding ever since. The expansion was not chaos. It was structure emerging from simplicity, energy cooling into matter, matter forming stars, and stars giving birth to life. The same laws that sculpted galaxies also shaped the atoms in human bodies. In the quiet halls of observatories, among the hum of instruments and the faint hiss of recorded starlight, humanity was encountering something sacred, the realization that the cosmos is not out there, but within us. We are, quite literally, the universe awakening to its own existence. And yet, even in that beauty, a shadow remained, a hint that something was missing. Einstein's blunder, as he called it, would one day be resurrected. The cosmological constant, the mysterious force he invented to keep the universe still, might not have been an error at all. It could be real, the invisible hand that drives the universe's accelerating expansion. But that revelation lay in the future, waiting for other generations, other telescopes, and other eyes to see. For now, in the 1920s and 30s, the universe had only just begun to reveal its motion, a faint whisper from the depths of time. Humanity stood at the threshold of a new cosmic order, a vision both humbling and infinite. From a single mountaintop, through a single lens, we had glimpsed the truth. The universe was not a painting. It was a symphony in motion. And in that revelation, the silence of eternity gave way to something greater. The first sound of cosmic awakening. The dawn of the unknown had begun. In the silence between galaxies, where no star burns and no planet turns, there exists a whisper, ancient, delicate, and eternal. It is not the voice of matter nor the hum of gravity, but the faint, ghostly echo of creation itself. A soft glow that fills the entire universe, the cosmic microwave background. It began not in a great observatory, nor in the depths of space, but in a field of pigeons and static. In 1965, two young radio astronomers, Arno Penzias and Robert Wilson, were calibrating a large horn-shaped antenna in Holmdel, New Jersey. It was built not for cosmology, but for communication. Part of a project once meant to listen to the stars of human technology, not the stars of the heavens. Yet in their data, a strange noise persisted, a faint hiss present at every direction, day or night, summer or winter. They tried everything. They recalibrated the instruments, cooled the receivers, removed interference, even cleared pigeon droppings from the antenna's interior. Still, the signal remained. Unrelenting, isotropic, eternal. What they had stumbled upon, by accident, was not a flaw, but a fossil, a glow from the birth of time itself. Thousands of miles away, at Princeton University, a small group of theorists led by Robert Dick and Jim Peebles had been searching for precisely this kind of radiation, the predicted relic of a once hot, dense universe. When Penzias and Wilson's discovery reached them, Dick reportedly turned to his team and said quietly, "Well, boys, we've been scooped. The universe had spoken, and what it said changed everything." That faint background hiss was the oldest light in existence, a remnant from when the universe was only 380,000 years old. Before that moment, the cosmos was a blinding fog, a plasma of particles and photons locked together in a furious incandescent soup. Space was so hot, so dense that light could not travel freely. It was scattered endlessly by electrons and protons, imprisoned in the cosmic fire. But as the universe expanded, it cooled. Eventually, the temperature dropped below 3000 Kelvin, cool enough for hydrogen atoms to form, for matter and radiation to separate. In that instant, light broke free. For the first time, photons could move unhindered across space. That light, released in a single cosmic breath, has been traveling ever since. Over billions of years, the expansion of the universe has stretched its wavelength from the bright glow of visible light to the soft hum of microwaves, cooled now to just 2.725 Kelvin above absolute zero. Yet despite its faintness, it fills all of space, wrapping every galaxy, every planet, and every life form in the ancient memory of the cosmos's birth. It is the fossil light of creation. When astronomers first analyzed it, they expected uniformity, a perfect, featureless glow, identical in every direction. But perfection is rarely natural. In 1992, NASA's COBE satellite, the Cosmic Background Explorer, revealed something extraordinary. Tiny ripples, subtle temperature variations across the sky, differences of just 1 part in 100,000. These faint patterns were not noise, they were structure. Encoded in them were the earliest imprints of quantum fluctuations, minute tremors in the fabric of reality that had been stretched by cosmic inflation during the first fractions of a second after the Big Bang. These tiny differences in density, where matter was ever so slightly thicker, became the seeds of everything that would ever exist. Over billions of years, gravity amplified them, pulling gas and dust together, igniting stars, building galaxies, sculpting the grand cosmic web. Every cluster, every star, every atom in our bodies can trace its origin to those delicate ripples frozen in the afterglow of creation. It is a story of immense simplicity and infinite depth. From the smallest quantum tremor, an entire universe arose. But as the data deepened, so too did the questions. After COBE came WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001. Its mission, to measure those ripples with 10 times greater precision. For 9 years, WMAP traced the afterglow with exquisite accuracy, painting the universe as it appeared when it was less than 500,000 years old. From this map, cosmologists read the very blueprint of reality, They measured the universe's age, 13.8 billion years. They calculated its geometry, perfectly flat on the largest scales, and they uncovered its composition. Only 4.9% of the cosmos is made of the matter we can see, the atoms that make stars, planets, and life. Another 26.8% is invisible, known only through its gravity, dark matter. And the remaining 68.3% is something far stranger, dark energy, a force driving the universe apart at an ever-accelerating rate. In the delicate patterns of the cosmic background, the universe had not only revealed its past, it had whispered the nature of its own existence. But the whisper was not without mystery. In 2013, the European Space Agency's Planck satellite produced the most detailed map yet of the cosmic microwave background. It confirmed the great truths of cosmology, but it also showed anomalies, small deviations that could not easily be explained, a slight cold spot, larger than predicted, an asymmetry between the northern and southern hemispheres of the sky, hints that perhaps the early universe was not entirely uniform, that something beyond our horizon might have left its mark. Were these mere statistical quirks, or were they the fingerprints of a deeper reality, collisions between universes, or echoes from before the Big Bang itself? No one knows. Each new observation brings greater precision, but also greater humility. The more clearly we see the universe, the more it resists final comprehension. In this light, the discovery of the cosmic background is more than science. It is a message written in the oldest language, the language of time itself. It tells us that we are not living in an eternal, unchanging cosmos. We live in a universe that was once young, bright, and alive with fire. A universe that remembers its own birth. When the first light broke free, there were no galaxies, no stars, no observers to witness it. Yet billions of years later, that same light fell upon Earth, into human instruments, into human minds capable of understanding its meaning. It is as if the universe had waited for intelligence to evolve so that it could finally be seen. The cosmic microwave background is more than a relic. It is a bridge across time. It connects the birth of the cosmos to the birth of awareness. In its faint glow lies the memory of all beginnings. A soft, endless hymn, older than any star. In the laboratories and observatories of today, scientists continue to study that whisper. Sensitive detectors measure its polarization, searching for the faint signature of gravitational waves, ripples in space-time produced during the first trillionth of a second after creation. If found, they would be the final confirmation of cosmic inflation, the mysterious burst that set the universe expanding faster than light. And yet, despite decades of study, the CMB retains its quiet enigma. Its existence confirms the Big Bang beyond doubt, but its subtle irregularities hint that there may have been something before it, some prelude to time. Physicists like Roger Penrose have speculated about a conformal cyclic universe, where each cosmic death gives rise to another Big Bang, a succession of aeons, each leaving faint imprints upon the next. Others explore quantum cosmology, suggesting that the universe may have tunneled into existence from a quantum vacuum. Its birth not a beginning, but a transformation. Each theory reaches for what the CMB only implies, that reality itself might be far older and far stranger than our imagination can yet hold. Still, amid these questions, one truth stands unmoved, that the universe carries its own memory. Every atom, every star, every heartbeat is a continuation of that first radiant moment. The cosmic microwave background is not just a scientific discovery, it is the echo of everything we are. When Penzias and Wilson first detected their mysterious hiss, they were listening to a chorus that had been singing for nearly 14 billion years, a music born not of strings or voices, but of photons released when the universe took its first breath. If one could translate that radiation into sound, it would be a single deep note, a cosmic hum resonating through all of space, timeless and unending. It is the sound of origin, the pulse of creation still beating beneath the stars. Today, satellites continue to listen. They scan the sky for new variations, new asymmetries, new whispers that might hint at what lies beyond. But perhaps, in that faint afterglow, we have already glimpsed something profound. That the universe is not random, but rhythmic. That every burst of starlight, every collision of galaxies, every thought in every mind is an echo of the same first fire. From the pigeons on a New Jersey antenna to the most distant quasars, all are connected by that invisible thread of ancient light. It binds us to the beginning and to each other. The discovery of the cosmic microwave background did not simply prove that the Big Bang occurred. It revealed that the universe remembers. That creation left behind not silence but a song that still plays quietly in the background of all existence, waiting for us to listen. In the grand tapestry of the cosmos, galaxies shine like jewels scattered across the dark. Their light, bright and ancient, tells stories of birth, of fire, of death. Yet behind that brilliance lies something unseen, something that does not shine, does not burn, and does not speak through the language of light. It is the invisible architecture of the universe, the silent scaffold that binds galaxies, anchors stars, and shapes the destiny of cosmic space itself. The story of dark matter begins not with what was seen, but with what was missing. In the 1970s, atop the thin air of Kitt Peak Observatory, a quiet revolution began. Astronomer Vera Rubin, together with Kent Ford, had been studying the rotation of spiral galaxies, immense pinwheels of stars turning slowly in the cosmic dark. According to Newton's laws, stars near a galaxy's center should orbit faster, while those farther out should drift more slowly, just as planets move around the sun. But Rubin's data told another story. When she measured the speed of stars along the outer edges of galaxies like Andromeda, she found that they were moving far too fast, almost as quickly as those near the center. The expected drop in velocity simply wasn't there. It was as if something unseen was adding mass, an invisible hand gripping the galaxies, holding them together against their own centrifugal force. Without this hidden matter, galaxies should have torn themselves apart long ago. At first, her results were met with skepticism. A woman working quietly in an era dominated by louder voices, Rubin's work was patient, meticulous, and precise, yet her data could not be dismissed. Every observation confirmed the same truth. Galaxies were rotating as if they were embedded in vast halos of unseen mass. She called it dark matter. It neither emitted nor absorbed light. It did not reflect, radiate, or glow. It was simply there, invisible, yet inescapable in its gravitational effect. What Rubin had uncovered was nothing less than the unseen structure of the cosmos. The idea of hidden mass wasn't entirely new. As early as the 1930s, Swiss astronomer Fritz Zwicky had observed that galaxies within the Coma cluster were moving too quickly to be held together by the visible matter alone. He proposed that some form of Dunkel Materie, dark matter, must be providing the extra gravity, but in his time, the concept was dismissed as an anomaly, an eccentricity of data. It would take Vera Rubin's quiet precision to turn Zwicky's speculation into undeniable evidence. Her work transformed cosmology. The visible stars and glowing gas were revealed as only a thin veil stretched over a hidden ocean of matter. Today, astronomers know that about 85% of all matter in the universe is dark. Everything familiar, every planet, star, nebula, and galaxy makes up less than 5% of existence. The rest remains unseen, silent, and utterly mysterious. But how can something that cannot be seen be known to exist? The answer lies in gravity, the one messenger that dark matter cannot disguise. Einstein's general relativity revealed that massive objects warp the fabric of space-time itself. When light from a distant galaxy passes near a cluster of galaxies, its path bends, creating arcs and distortions, a phenomenon called gravitational lensing. Astronomers began to notice that these distortions were far stronger than the visible matter could account for. The light of the cosmos was bending not just around galaxies, but around something far greater, an invisible mass enshrouding them. In the Bullet cluster, two colliding groups of galaxies became one of the most striking proofs of dark matter's existence. When observed in visible light, the galaxies appeared in one location. When mapped in X-rays, the hot gas, containing most of the normal matter, lay elsewhere. But when their gravitational lensing was measured, the invisible mass appeared separate, aligning not with the gas, but with the galaxies themselves. It was as if the luminous world had been displaced, while the shadow world remained intact, a ghostly twin overlaying the visible cosmos. The conclusion was unmistakable. Most of the universe's matter does not shine. For decades, physicists have searched for what dark matter actually is. They imagined it might consist of exotic particles born in the first moments after the Big Bang, relics of a colder, stranger physics than anything we have yet observed. Among the leading candidates were WIMPs, weakly interacting massive particles. They would drift invisibly through the universe, barely touching ordinary matter, like phantoms passing through walls. Vast detectors buried deep underground, in abandoned mines and beneath mountains, were built to find them. These experiments, shielded from cosmic rays and noise, waited for the faintest flash of interaction. Years passed, decades, no signal came. Then came new ideas, axions, ultra-light particles that could fill the cosmos like a soft wave, and sterile neutrinos, ghostly cousins of known particles that might account for the missing mass. Each theory was elegant, each test carefully designed, but the silence continued. The deeper humanity looked, the more elusive the darkness became. Some began to wonder, what if the darkness was not made of particles at all? What if the laws of gravity themselves were incomplete? Theoretical physicists proposed modified Newtonian dynamics, or MOND, suggesting that at vast cosmic distances, gravity behaves differently than Einstein described. Others explored FR gravity, or theories involving extra dimensions, in which the apparent mass of dark matter might emerge from the geometry of space-time itself. Yet none of these alternatives have fully matched the observations. Dark matter, for all its invisibility, continues to predict the structure of galaxies, the formation of clusters, and the evolution of the universe with uncanny accuracy. It behaves as if it is truly there. Vast, silent, and gravitationally real. Still, its nature remains unknown. From the smallest galaxies to the largest cosmic structures, dark matter acts as the skeleton of existence. In the early universe, it began to clump before ordinary matter could cool enough to form atoms. It gathered into halos, invisible frameworks around which gas accumulated, condensed, and ignited into the first stars. Without dark matter, galaxies might never have formed at all. It is the cosmic architect, the hidden weaver of the grand design. Simulations of the universe, immense digital recreations run on supercomputers, show its influence clearly. Without dark matter, there is only chaos and emptiness. With it, the cosmos forms a vast cosmic web, filaments of matter stretching hundreds of millions of light years, connecting galaxies like beads along threads of gravity. It is a universe sculpted not by light, but by shadow, and yet the paradox grows deeper. For something so dominant, dark matter is almost completely indifferent to us. It passes through the earth, through our bodies, through the atoms of our own blood, without leaving a trace. Trillions of its particles, if particles they are, drift through each of us every second, as if we were transparent. In laboratories across the world, from Italy's Gran Sasso to China's Jinping Underground Laboratory, scientists listen for a whisper that never comes. Their detectors sit in stillness, surrounded by rock and silence, waiting for a glimmer that might prove that darkness has form. But the silence endures. The unease grows. If dark matter cannot be detected, cannot be seen and cannot be felt, then what is it? Is it something physical or a reflection of physics itself? A symptom of a universe whose true rules remain just beyond comprehension? Perhaps dark matter is not matter at all, but a manifestation of unseen dimensions, a hidden curvature in the geometry of space-time. Perhaps it is energy trapped in another form, leaking into our universe only through gravity. Or perhaps, as some whisper, the darkness is a mirror, a shadow cosmos overlapping ours, invisible but parallel, existing in the same space, responding only to its own kind. Speculation dances at the edge of knowledge, but one truth remains: the visible universe, all the galaxies, stars, and light is but a thin film upon a much deeper reality. In the end, Vera Rubin's quiet observation became one of the most profound discoveries in the history of science. Her curves, drawn in ink on fragile paper, redrew the cosmos itself. She revealed that what we see is not what truly exists. In a universe that appears luminous and vibrant, most of it lies forever in shadow. Dark matter does not glow, yet it governs the dance of galaxies. It does not speak, yet it dictates the shape of space. It does not shine, yet it holds the stars together. It is the silent majority of existence. the unseen hand that guides the cosmos through its long and restless expansion. Perhaps, one day, humanity will capture a particle of that darkness and hold in its grasp the key to the hidden half of reality. But even if that day never comes, the truth remains awe-inspiring. We live in a universe that is mostly invisible, a place where light is the exception and darkness is the rule. And in that darkness lies the greatest secret of all, the unseen fabric from which everything we know was woven. In the final years of the 20th century, the universe revealed a secret so profound that it shattered the very foundation of modern cosmology, a discovery born not from grand machinery or ancient relics, but from faint, dying stars, cosmic candles burning billions of light years away. These were Type Ia supernovae, the predictable detonations of white dwarfs, the last breaths of sun-like stars collapsing under their own weight, then reigniting in a final blaze of fury. For decades, astronomers had used these explosions as standard beacons of distance. Their light, unchanging in brilliance, could reveal how far the galaxies that hosted them truly were. But in 1998, two rival teams, the Supernova Cosmology Project led by Saul Perlmutter and the High Z Supernova Search Team led by Brian Schmidt and Adam Rees, set out to answer a single, ancient question: how fast is the universe slowing down? Since Hubble's revelation in 1929, it had been known that the universe was expanding. The galaxies, once thought eternal and fixed, were in fact receding, like glowing embers carried away on an unseen tide of space itself. The force of the Big Bang was assumed to be weakening with time, its momentum resisted by gravity, the universal tug of matter pulling everything back together. Yet when the supernovae data arrived, the light from those distant explosions told a story no one was prepared to believe. The galaxies weren't slowing down, they were speeding up. The universe, it seemed, was not gently coasting into stillness. It was accelerating, racing apart faster and faster, as though pushed by an invisible hand. The shock reverberated through science like a cosmic thunderclap. If true, it meant that some mysterious energy was woven into the very fabric of space. A force that repelled rather than attracted, driving galaxies away from each other with ever-increasing speed. This was the birth of dark energy, a term that captures both its mystery and its power. It was invisible, immeasurable, and yet it dominated everything. Today, it is estimated that dark energy makes up nearly 70% of the total energy of the universe, far outweighing all the galaxies, stars and dark matter combined, and yet it cannot be seen, touched, or directly measured. It reveals itself only in the way space stretches between galaxies, in the accelerating expansion of everything that exists. To understand what dark energy is, one must first grasp what it does. Imagine the universe as a vast, elastic fabric, a cosmic balloon being blown up from within. Each galaxy is like a dot on its surface. As the balloon expands, the dots move farther apart, not because they themselves are moving, but because space itself is stretching. At first, that expansion was thought to be slowing under the pull of gravity, the collective attraction of all matter and energy. But dark energy acts as a kind of anti-gravity. The more space expands, the more of it there is, and the more repulsive force is generated. This strange feedback drives the universe to accelerate, faster with every passing eon. The galaxies are not just drifting apart, they are being driven apart, carried away on a tide of energy embedded in space-time itself. To many physicists, the discovery felt eerily familiar, because decades earlier, Albert Einstein had introduced something remarkably similar: the cosmological constant, a mathematical term he added to his equations of general relativity in 1917. At the time, Einstein, like most scientists of his era, believed the universe was static and eternal. But his equations predicted something unsettling: that gravity, left unchecked, would cause the cosmos to collapse. To counter this, he introduced a balancing term: a repulsive force, a kind of built-in pressure of space that kept everything stable. When Edwin Hubble later proved that the universe was expanding, Einstein famously called the constant his greatest blunder. Yet now, more than half a century later, that same discarded idea returned, not as a mistake, but as a revelation. What Einstein once introduced for mathematical convenience might, in fact, be real. a property of space itself. Empty space, it seemed, was not truly empty at all. According to quantum field theory, the vacuum is teeming with energy, the restless fluctuations of invisible fields that fill all of existence. Particles and antiparticles briefly wink into being and vanish again, their energy adding up to a subtle, persistent pressure. If even a fraction of that vacuum energy contributes to the fabric of space, it could explain the accelerating expansion. But here lies the great paradox. The predicted energy from quantum theory is 120 orders of magnitude larger than what cosmologists observe. It is the most severe discrepancy in all of physics, a mismatch so extreme that it defies imagination. Somewhere between the language of quantum mechanics and the geometry of space-time, a truth remains hidden. Dark energy is the signpost pointing toward that truth. As scientists refined their observations, the evidence became undeniable. The Planck spacecraft, mapping the faint relic light of the cosmic microwave background, revealed a universe perfectly consistent with one dominated by dark energy. The geometry of the cosmos itself, flat on the largest scales, demanded a mysterious component to balance its energy density. Supernova after supernova told the same story. The light was too faint, the distances too great. The expansion was indeed accelerating. The universe, it seemed, was not simply expanding into the void itself was expanding into us. On the grandest scales, this revelation transformed the fate of the cosmos. If dark energy remains constant, galaxies will continue to drift apart forever. The night sky, billions of years from now, will grow darker and lonelier. Distant galaxies will fade from view, redshifted beyond detection, their light stretched into invisibility by the relentless growth of space. In that far future, the Milky Way and its neighbors may merge into one great island galaxy, surrounded by endless blackness. A solitary archipelago adrift in an expanding sea. This possible destiny has been called the Big Freeze. Stars will burn out, galaxies will fade, and the universe will cool toward absolute zero, not with a bang, but with a long, silent sigh. But what if dark energy changes with time? Some theories suggest it might not be constant at all. It could evolve, intensify, or decay, a dynamic field often called quintessence. If it grows stronger, it could one day rip the cosmos apart in a cataclysmic finale, a big rip, where galaxies, stars, planets, and even atoms are torn asunder as space-time itself fractures. Or perhaps dark energy will weaken, allowing gravity to reclaim its throne, pulling the universe back into a fiery big crunch. Each possibility lies encoded within the laws of physics, but the true fate remains a mystery suspended between equations and eternity. Beyond its physical meaning, the discovery of dark energy carries a haunting philosophical weight. For centuries, humanity has looked to the heavens and seen a universe governed by gravity, a cosmos that pulls together, that gathers and binds. But the revelation of dark energy paints a different picture, a universe that is not uniting, but fleeing from itself. Galaxies are not drawn together, but cast apart. The deeper we look, the faster they run. It is as if the universe were an ancient memory, expanding away from its own origin, chasing an ever-distant horizon that can never be reached. In this light, dark energy becomes more than a force. It becomes a symbol of cosmic restlessness, a reflection of impermanence written on the largest possible canvas. And yet, the story of dark energy is still being written. New missions, like the Euclid Space Telescope and NASA's Nancy Grace Roman Observatory, now seek to map the shape of the cosmos with unprecedented precision. By studying the subtle distortions of galaxies, the clustering of matter, and the flicker of distant supernovae, they hope to unravel the nature of this invisible energy. Some suspect that dark energy is the true face of Einstein's cosmological constant, a quiet, eternal pressure of the vacuum itself. Others believe it hides a deeper symmetry, or perhaps a new field that interacts with matter in ways we have not yet imagined. But whatever its nature, it speaks of a universe far stranger than ever dreamed, a cosmos where nothingness possesses power, where the void itself creates motion, where the very emptiness between stars is alive with unseen energy. In the quiet halls of observatories, and the deep silence of space telescopes adrift in orbit, this mystery endures. The data continue to arrive, numbers, light curves, spectra, each one whispering the same haunting refrain. The universe is accelerating. It is not simply vast, it is not static. It is restless, propelled by a force that no one yet understands, toward a future that no one can yet see. The galaxies flee, the darkness grows, and time stretches onward. Dark energy is the breath of that expansion, the unrelenting pulse of a cosmos still unfolding, still rewriting its own beginning, and as humanity looks upward, seeking to understand the power that drives the stars apart, one question echoes through the emptiness. What if the universe itself is alive, forever yearning, forever expanding, fleeing not from something, but toward the infinite possibility of what it might one day become? In science, there are discoveries that expand human understanding, and there are those that fracture it. The revelation of dark energy did both. It was not merely a new piece in the cosmic puzzle. It was the unsettling realization that the puzzle itself might never fit together. The universe, once thought to be orderly and comprehensible, had begun to betray its own rules. For centuries, the foundation of cosmology rested upon a simple, elegant assumption, the cosmological principle. It stated that on the largest scales, the universe is homogeneous and isotropic, the same everywhere, in every direction. There are no privileged places, no cosmic center, no special vantage point. It was the ultimate expression of humility in science, the belief that humanity, and even our own galaxy, occupies no unique position in the grand cosmic design. But as the 20th century faded into the 21st, that comforting symmetry began to tremble. The accelerating expansion of space, driven by dark energy, hinted that something profound was broken. If dark energy permeates every region of the cosmos, then why does it behave so precisely, so uniformly across billions of light years? If it is a property of the vacuum itself, why does it possess just the right value? Not enough to tear galaxies apart in their infancy, not too little to halt the universe's expansion altogether. It seemed as though the universe had been fine-tuned to an impossible degree, balanced on a knife's edge between chaos and stillness. Physicists turned to the one framework that had never failed them before, quantum field theory. According to this theory, even empty space is not truly empty. It seethes with vacuum energy, the restless dance of quantum fields that fluctuate constantly, birthing and annihilating particles in an eternal rhythm. Every field in the quantum realm contributes to this vacuum energy. The electromagnetic field, the Higgs field, the gluon fields that bind atomic nuclei together. Add up all these contributions, and one should arrive at the true energy density of empty space, the cosmological constant that drives the universe's expansion. But when the numbers were calculated, what emerged was an absurdity. The predicted energy of the vacuum was 120 orders of magnitude larger than what astronomers actually observed. A number so vast, it defies comprehension. A 1 followed by 120 zeros. In physics, this is known as the cosmological constant problem, and it is the most catastrophic mismatch between theory and observation in the history of science. If quantum theory were correct, the universe should have exploded itself into oblivion long before stars or galaxies could ever form. And yet, here it stands, stable, expanding gently. Filled with structure, light, and life, the equations say it should not exist. And yet it does. This was not merely a mathematical inconvenience. It was an existential paradox. Physicists began to wonder if the very principles of reality were incomplete. Perhaps the vacuum energy was being cancelled or hidden by some unknown symmetry. Perhaps dark energy was not a constant at all, but a dynamic field, a ghostly fluid that evolves as the cosmos expands. Others reached for even more unsettling possibilities. Maybe our universe is not alone. The idea of a multiverse, once a fringe speculation, began to surface in serious conversation. If countless universes exist, each with different laws, constants, and energies, then perhaps ours is simply one of the rare few in which the vacuum energy happens to be small enough for matter and life to form. In this view, we do not inhabit a typical universe at all, but a profoundly unlikely one, a cosmic oasis within a vast desert of impossible realities. To some, This explanation felt deeply unsatisfying, a retreat from the search for physical truth into the realm of probability. But to others, it was a glimpse into the deeper architecture of existence itself. A universe selected, not designed, by the fragile condition of its own survival. The more scientists studied dark energy, the more it seemed to violate everything they thought they understood about nature. The universe appeared eerily smooth on large scales, its expansion uniform, its geometry nearly flat, its balance of forces astonishingly precise. Yet beneath that serenity lies chaos, quantum fluctuations, vacuum fields, and the ghostly remnants of a universe that should have collapsed under its own contradictions. In the laboratory, particle accelerators probe the smallest scales of matter, colliding protons at energies once found only in the first moments after the Big Bang. Physicists at CERN, Fermilab, and laboratories around the world continue to seek any sign of the mechanism behind this cosmic acceleration. Could it be tied to the Higgs field, discovered in 2012, whose invisible energy permeates all of space? Could dark energy emerge from a hidden dimension, a wrinkle in space-time unseen by our senses? Or could it be that Einstein's equations themselves are incomplete? That the very geometry of the cosmos bends differently at the edges of infinity? Each hypothesis opens a door to deeper mystery. Each door leads to more silence. The emotional weight of this realization ripples far beyond mathematics. For the first time, humanity faces the possibility that the known universe, the stars, the planets, the atoms, even light itself, makes up less than 5% of reality. The rest, 95%, is made of dark matter and dark energy. Entities that neither emit nor absorb light, that cannot be seen or touched, but that dictate the motion of galaxies and the fate of time itself. Everything humanity has ever known, every civilization, every discovery, every dream, exists within a thin film of visible matter, suspended in an invisible ocean whose depths we cannot yet comprehend. The mind resists this truth. It seeks pattern and meaning, certainty and cause. But the cosmos offers instead a whisper, that the laws we hold sacred are themselves only approximations, faint shadows of a deeper order still hidden beneath the surface of being. And so, physics, the most precise science ever created, stands humbled before its own ignorance. The universe, once thought to be governed by simplicity and symmetry, now appears to be fine-tuned beyond imagination. The constants of nature, the strength of gravity, the mass of the electron, the rate of cosmic expansion are balanced so delicately that even the slightest deviation would erase the possibility of life. Is this coincidence, or is it a clue? Some speak of the anthropic principle, the notion that we can only observe a universe compatible with our existence. Others reject this as surrender, a poetic way of saying we simply don't know. But perhaps that is the point. Perhaps the greatest shock of all is not that the universe defies explanation, but that it invites us to question what explanation truly means. The discovery of dark energy did not close the book on cosmology. It opened a new one, a volume written in symbols humanity has not yet learned to read. Each observation, each equation, each glimmer of understanding leads not to certainty, but to wonder. The cosmos seems to whisper that knowledge itself has limits, that reality may be stranger, more profound and more infinite than any theory could ever contain. And yet, amid that vast uncertainty, there remains beauty. The same force that tears galaxies apart also allows them to form. The same emptiness that defies reason also makes space for creation. The same universe that resists comprehension continues to exist, luminous, expanding, alive. In the stillness between galaxies, in the silence of the vacuum lies the greatest paradox of all, that the void is not nothing, it is everything. It holds the hidden structure of reality, the invisible pulse of expansion, the very energy of existence itself. The universe, in its quiet defiance, reminds us that to seek understanding is not to conquer mystery, but to embrace it. For in the moment, we think we understand it. The cosmos changes shape, a mirror shattering into deeper infinities. And so, beneath the elegance of our equations and the brilliance of our discoveries, one truth endures. That humanity stands at the threshold of knowledge, gazing into the darkness, a darkness not of ignorance, but of potential, a darkness that is not empty, but waiting to be known. Chapter 6. Peering Deeper. The instruments that redefined reality. In the great silence between galaxies, where the light of ancient suns fades into oblivion, humanity has learned to build new eyes. Eyes that pierce the abyss and transform darkness into knowledge. For centuries, the night sky was an untouchable canvas, a glittering sea of mystery painted across the firmament. But then came the machines, metallic extensions of curiosity, forged from precision and mathematics, crafted to see beyond human frailty. The first of these great instruments to truly shift the cosmic gaze was the Hubble Space Telescope. Launched in 1990, it rose beyond Earth's turbulent veil of atmosphere, where starlight blurs and bends, into the pristine blackness of orbit. From there, it began to watch, patiently, silently, collecting light that had journeyed for billions of years. When Hubble's mirror was first revealed to be flawed, humanity's dream of perfect cosmic vision trembled. Yet the flaw was not the end, it was a beginning. In 1993, astronauts carried tools and courage into space itself, repairing Hubble's sight with a precision that bordered on the poetic. When its corrected lens opened again, the universe unveiled itself in ways no human had ever imagined. Then came the deep field. A single dark patch of sky, seemingly empty, insignificant, was chosen at random. For 10 consecutive days, Hubble stared into that void. The result was nothing short of revelation. In that blackness, over 10,000 galaxies emerged, each a collection of billions of stars, each a fragment of cosmic history. What had once appeared as nothing was, in truth, the everything. The Hubble Deep Field became a window into the infancy of existence, a mirror reflecting the boundless richness of the cosmos. Every pixel of that image was time itself, the light of ancient suns, born when Earth did not yet exist, reaching across billions of years to tell their story. Astronomers wept, not because they found answers, but because they realized how small every question had been. Yet even Hubble, the telescope that changed human sight, could not glimpse the moment of cosmic dawn, the time when the first stars ignited within the cooling fog of creation. The universe, in its earliest light, remained hidden behind veils of infrared shadow, wavelengths too long for Hubble's gaze to see. And so, humanity built another eye, one capable of catching the whispers of that first light. The James Webb Space Telescope, a golden mirror born from 3 decades of ambition, became the most intricate instrument ever placed in the cold silence of space. Webb unfolded itself a million miles from Earth, like a cosmic origami, each mirror segment aligning with atomic precision, each golden petal designed to gather light from the universe's first dawn. Its infrared vision could see what Hubble could not, the faint warmth of infant galaxies, born less than 300 million years after the Big Bang. When Webb's first images were released, the universe changed again. In the deep red glows of distant galaxies, astronomers found structures, spiral forms, clusters, and disks that should not have existed so early. The cosmos, it seemed, had built itself faster, more efficiently, and more mysteriously than expected. Every discovery Webb made raised a deeper question. Had we misunderstood cosmic time itself? Each infrared frame is not merely an image. It is a relic of time travel, a photograph taken billions of years before human eyes existed to behold it. Webb peers so far back that it nearly touches the afterglow of creation, a silent witness to the birth of light itself. But the story of humanity's vision is not confined to the cold vacuum of space. On Earth, among deserts and mountaintops, other instruments gaze skyward, their lenses and mirrors cradled beneath domes of glass and steel. These are the sentinels of the ground, vast observatories built to map the invisible scaffolding of the universe. At Chile's high plateaus, the Vera C. Rubin Observatory prepares to scan the entire sky every few nights, a digital heartbeat that will record the motions of billions of stars and galaxies. Its project, the Legacy Survey of Space and Time, LSST, will generate the largest cinematic record of the cosmos ever attempted, a moving portrait of a living universe. Farther north, the Dark Energy Spectroscopic Instrument, DESI, listens not for light, but for the structure it reveals. Using the spectra of over 35 million galaxies, DESI traces how matter is stretched and woven by cosmic expansion. an intricate pattern sculpted by the mysterious force known as dark energy. And beyond Earth's atmosphere, the Euclid mission, a collaboration led by the European Space Agency, now maps the geometry of the universe itself. Euclid peers into deep time, measuring how galaxies cluster and bend the light that passes through them. Through gravitational lensing, it sketches the outline of an invisible architecture, the cosmic web. The cosmic web is perhaps the most haunting revelation of all. Across the unimaginable vastness of space, galaxies are not scattered randomly. They are arranged like beads upon filaments, connected through gravitational threads of dark matter. These filaments stretch across billions of light years, forming a structure so immense that even clusters of galaxies appear as dust motes suspended in a luminous fog. Simulations, guided by data from DESI, Euclid, and Rubin, reveal a universe woven like a living fabric, with voids vast enough to swallow thousands of Milky Ways, and filaments glowing faintly with the energy of ancient collisions. If one could step back and see the universe in its entirety, it would appear like a colossal brain, a network of cosmic neurons firing across eternity. Every connection, every bridge of gravity, is a record of invisible interactions. Dark matter, though unseen, acts as the gravitational skeleton upon which the luminous flesh of galaxies takes form. Without it, the cosmos would be unrecognizable, dispersed, and cold, a chaos without structure. But while these machines of light map the visible and the unseen, a new generation of instruments has begun listening to something different. Not light, but the trembling of space itself. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected ripples in space-time, gravitational waves, predicted a century earlier by Einstein's equations. These waves were born from the collision of two black holes, each distorting the fabric of reality as they merged. It was the first time humanity heard the universe, not through light, but through gravity itself. Since then, observatories like Virgo and Cagra, along with proposed space-based detectors like LISA, have begun expanding this new sense, turning the cosmos into a symphony of space-time vibrations. Through these gravitational echoes, scientists hope to glimpse the earliest moments after the Big Bang, an era before light could even exist. Every signal, every wave, is a whisper from a part of the universe no telescope can see. Together they form a bridge, linking what is visible, what is invisible, and what is yet to be known. Across these technological marvels, from Hubble's glassy gaze to Webb's golden lattice, from Rubin's nightly symphony to LIGO's trembling space-time, runs a single thread: humanity's yearning to understand. Each instrument is not merely a tool, but a reflection of our own nature, the desire to reach beyond limitation, to see what the eyes were never built to see. These machines are more than metal and code. They are extensions of thought itself. They translate photons into memory, gravity into melody, and emptiness into meaning. Through them, the universe reveals not only its distant past, but its profound connection to us, creatures of dust who dare to look into infinity and call it home. And yet, every revelation brings with it a shadow. The deeper the instruments peer, the stranger the universe becomes. Webb's early galaxies that should not exist, Euclid's hints of missing matter, gravitational signals that arrive before theory expects them. Each clue points to a cosmos that refuses to be fully understood. Perhaps, in the end, these instruments are not only revealing the nature of the universe, but exposing the limits of human perception itself. In their lenses, sensors, and mirrors, humanity confronts its own reflection, fragile, brilliant, and endlessly curious. The universe is not silent, it speaks. In wavelengths of light, in ripples of space-time, in the faint hum of background radiation echoing from creation. And we have built the instruments to listen. For as long as we dare to look deeper, the cosmos will continue to whisper back, reminding us that even in the coldest reaches of infinity, awareness itself is the universe made visible. Chapter 7. The Great Tension. Conflicting realities. In the stillness between galaxies, where cosmic expansion stretches light into whispers of red, a quiet disagreement has begun to fracture the harmony of modern cosmology. It is a tension not of ideology, but of reality itself, a rift between two ways of measuring the universe's growth. For decades, the expansion of the cosmos seemed a settled truth, an elegant rhythm established by observation and theory. The Hubble constant, that single number describing how fast the universe expands, was thought to unite our understanding of space, time, and history. Yet now that unity is breaking apart. Two measures, two truths, both drawn from the cosmos, and both refusing to agree. The first measure comes from the near and familiar, the local universe. Astronomers study the pulsating stars called Cepheid variables, cosmic lighthouses whose rhythm of brightness reveals their distance. They then turn to Type Ia supernovae, explosions so bright and consistent they serve as markers of space itself. By measuring how far these brilliant detonations lie and how quickly their light is redshifted, scientists can determine how fast the universe is expanding today. Their result, roughly 73 kilometers per second per megaparsec. For every million parsecs, about 3.26 million light years, space itself expands by 73 kilometers each second. But when cosmologists turn their gaze backward in time, toward the cosmic microwave background, a very different number appears. This ancient radiation, the fossil light of the Big Bang, encodes the early conditions of the universe. The Planck satellite, launched by the European Space Agency, mapped this background with exquisite precision. By fitting the data to the model of the Big Bang, Planck revealed a slower expansion, 67 kilometers per second per megaparsec. A difference of merely 6 may seem small, yet in the precise mathematics of the cosmos, it is enormous. It is a gap that no known error can explain. It is as if the universe were whispering two different stories about itself, one ancient, one modern, and neither willing to yield. This mystery is now known as the Hubble tension, a conflict that strikes at the foundation of cosmology itself. In laboratories and observatories across the world, scientists have checked and rechecked their data. They have recalibrated telescopes, reanalyzed Cepheid stars, remeasured cosmic distances, and refined every constant that feeds the equations. Still, the rift remains. Some suspect the problem lies not with the measurements, but with the model. Perhaps the universe is not the simple, elegant system Einstein once described. Perhaps something new and unseen is shaping the expansion of space. At the heart of Einstein's equations lies a fragile assumption that gravity behaves the same everywhere, always. But what if this is not entirely true? In the 1980s, physicist Mordechai Milgram proposed an alternative, modified Newtonian dynamics, or MOND. He suggested that at the faintest accelerations, far weaker than anything experienced on Earth, gravity may deviate from Newton's or Einstein's laws. In galaxies, this subtle shift could explain the strange motions of stars, motions often attributed to invisible dark matter. Later, theorists expanded this idea into frameworks like FR gravity, in which the curvature of spacetime responds in more complex ways to matter and energy. In such models, gravity itself becomes dynamic, evolving, flexible, perhaps even self-correcting. If gravity behaves differently on cosmic scales, the expansion of the universe may not be uniform. The discrepancy between the early and late measurements could be the echo of this deeper truth, a sign that Einstein's great equation, though beautiful, is incomplete. Others turn their attention to a more elusive culprit: dark energy. Since its discovery in 1998, dark energy has been treated as a constant, an unchanging pressure within the fabric of space-time, driving galaxies apart. But what if that constant is not constant at all? A growing number of physicists propose the idea of dynamic dark energy, or quintessence, a cosmic field that evolves over time, changing the rate of expansion as the universe matures. In this view, dark energy is not a static property of the vacuum, but a living component of reality, waxing and waning, perhaps even interacting with dark matter. If so, the early universe, observed through the cosmic microwave background, may have been governed by a different dark energy density than the one shaping the cosmos today. The Hubble tension, then, becomes not a flaw in observation, but the first hint of cosmic evolution on scales we are only beginning to imagine. Deep beneath mountains and deserts, new experiments are being built to test these ideas: gravitational wave detectors, precision telescopes, and cosmic surveys from DESI to Euclid. From the Vera Rubin Observatory to JWST are joining the effort to map expansion across every epoch of cosmic history. They seek the fingerprints of quintessence, subtle shifts in the clustering of galaxies, tiny deviations in the rate of expansion, whispers in the cosmic web that betray the movement of an unseen field. Each observation is a thread in a larger tapestry, a puzzle spanning from the birth of the first light to the accelerating age we inhabit now. Yet, as data grows, so does the unease. The universe seems to resist the simplicity of human understanding. If the Hubble tension cannot be explained by measurement or by known physics, then it may point to something even more profound, a rupture in the very framework of cosmology. Perhaps the cosmological principle, the sacred assumption that the universe is the same in every direction, is beginning to break. Maybe our corner of the cosmos is not typical. Perhaps it sits within a subtle gravitational bubble, a local void or overdensity that alters the way space expands around us. If true, this would mean that the universe we observe is not an average sample, but a cosmic outlier, a skewed perspective from a unique vantage point. The tension, then, would not be universal, but local, a reminder that even the grandest theories must account for our particular place within the cosmic fabric. Behind every possibility, one haunting question persists. What if the laws of physics themselves are not fixed? Quantum field theory predicts an energy density of the vacuum, the so-called zero-point energy, that exceeds the observed cosmological constant by 120 orders of magnitude. It is the largest mismatch between theory and observation in the history of science. If this vacuum energy were even slightly higher, galaxies could never have formed, stars would not have ignited, life could not exist. That it is so finely balanced, small enough to allow structure, large enough to accelerate expansion, defies comprehension. Some call it coincidence, others whisper of fine-tuning, the idea that the universe, through some unknown principle, selected conditions that allow its own observers to arise. The Hubble tension may be another expression of this delicate balance, a symptom of an underlying order we cannot yet name. In the quiet halls of observatories and research centers, physicists confront a sobering possibility. Perhaps the universe is stranger than even their equations can contain. Einstein's relativity reshaped space and time. Quantum mechanics shattered certainty itself. Yet now both pillars stand uneasy, two realms of theory that cannot reconcile. Between them lies the tension of the cosmos, a gulf of understanding as vast as the voids between galaxies. The conflict of numbers, 73 and 67, may seem trivial compared to the scale of creation, but within it could lie the seed of the next great revolution, a doorway into physics beyond the horizon of human thought. There is a growing realization that science may be approaching the limits of its current map. The expansion of the universe is no longer a smooth story. It has become a question that stares back, a cosmic mirror reflecting the limits of comprehension. Each new telescope refines the image. Each dataset deepens the paradox, and somewhere, hidden in the difference between two measurements, may rest the first glimpse of a deeper reality, a universe whose laws bend and breathe, whose constants are not constant, whose story is still being written. The cosmos is vast enough to hold contradictions, yet precise enough to reveal them. Its expansion carries not only galaxies, but also the weight of doubt, the sense that even now, after a century of discovery, humanity stands at the threshold of something it cannot yet name. In the tension between two numbers lies a quiet truth. The universe does not exist to be solved. It exists to be witnessed, evolving, expanding, defying, and whispering through the silence of eternity. And perhaps one day, when instruments have grown more sensitive and minds more patient, the discord will resolve, not into simplicity, but into a harmony beyond comprehension. Until then, the great tension remains, a pulse at the heart of reality, a reminder that the cosmos, like consciousness itself, is not merely expanding, it is becoming. Chapter 8. The Edge of Understanding, the Multiverse. Hypothesis beyond the farthest galaxies, beyond the final echoes of light from the Big Bang, lies an idea that stretches the imagination to its breaking point, the possibility that this universe may not be the only one. It begins not with fantasy, but with physics, with a moment so brief it cannot be measured, and yet so powerful that it gave rise to all of space and time. More than 13.8 billion years ago, the newborn cosmos expanded, Not gently, but violently. In a fraction of a second, it swelled from a subatomic scale to something vast, smoother, flatter, and colder than anything that could have formed, through ordinary explosion. This theory is called cosmic inflation. First, proposed in 1980 by physicist Alan Guth, it solved the deepest riddles of cosmology. Why the universe looks the same in all directions. Why distant regions, too far apart to have exchanged light, share nearly identical temperatures. Why space itself seems so perfectly balanced between expansion and collapse. Inflation explained it all by suggesting that, in its first instant, the universe expanded exponentially, faster than the speed of light itself. But inflation did more than solve old problems. It opened a door to something far stranger. If space could inflate once, could it happen again? Quantum theory says that even the vacuum is never truly empty. Tiny fluctuations, fleeting ripples of energy, constantly emerge and vanish in the sea of nothingness. During inflation, these fluctuations could be magnified to cosmic scales, becoming the seeds of galaxies and stars. But according to some versions of inflation theory, this process never truly ends. While one region, like ours, might slow, cool, and become a universe filled with galaxies and light, other regions may continue inflating endlessly. This is eternal inflation, a universe that is not a single bubble of existence, but an infinite froth of them. Each bubble, each region of space where inflation has stopped, could form its own cosmos, with its own laws of physics, its own constants, even its own version of reality, and thus emerges one of the most daring ideas in all of science: the multiverse. In this vision, the universe we see through telescopes is just one drop in a boundless cosmic ocean. Around it, unseen, unreachable, other universes bloom like stars in an eternal field. Some may be sterile, collapsing moments after birth. Others may burn too fiercely for life to take hold. And some, perhaps a few, find the fragile balance that allows complexity to unfold, where gravity, chemistry, and time align in just the right harmony to give rise to observers like us. To some, this idea offers a profound explanation for one of the greatest puzzles in science: the fine-tuning of the cosmos. The constants of nature, the strength of gravity, the charge of the electron, the rate of cosmic expansion, seem calibrated with impossible precision. Change any one of them, even slightly, and stars would not form, atoms would not bind, and life would never emerge. Why then do these numbers appear so perfect? The anthropic principle offers one possible answer. Perhaps there is nothing special about these values at all. If countless universes exist, each with different laws, then it is only in a rare few that conditions permit the emergence of consciousness. And naturally, it is within one of those few that beings arise to ask the question at all. In this sense, the fine-tuning of the universe is not design. It is survival bias, a reflection not of intent but of existence. The idea is as poetic as it is unsettling, for it suggests that everything known, every law of nature, every constant of reality, may be but one variation among an infinite symphony of possibilities. Yet, as elegant as the idea may seem, it is haunted by one question: can something beyond our universe ever be proven? The multiverse, by its very nature, defies direct observation. Each cosmic bubble is separated by realms of inflating space expanding faster than light, a barrier that no signal, no particle, no force can ever cross. To detect another universe would be to break the very boundaries that define ours. And so, for now, the evidence remains hidden behind an impenetrable veil. Still, physicists continue to search for subtle fingerprints, faint signs that the cosmic fabric once brushed against another realm. Some look for anomalies in the cosmic microwave background, circular imprints or temperature irregularities that could hint at collisions between universes long ago. Others study gravitational waves, hoping to find patterns left behind by inflation itself, echoes of the birth of countless worlds. So far, the evidence is inconclusive. The universe remains silent, but silence is not the same as absence. Among the most haunting aspects of this idea lies the role of dark energy, the mysterious force that drives cosmic acceleration. How could dark energy be more than just an invisible pressure? Could it be the manifestation of a deeper field, the same one that powered inflation now lingering in a weakened form. Some cosmologists propose that dark energy might vary from universe to universe, each bubble possessing its own version of the vacuum. A different energy density, a different fate. In one, dark energy might be strong enough to tear space apart. In another, too weak to overcome gravity, leading to eventual collapse. And in ours, perfectly balanced, just enough to allow life to arise before the darkness takes hold. If this is true, dark energy may be the fingerprint of our cosmic lineage, the clue to which branch of the multiverse we inhabit. It may even hint that our universe is not isolated, but connected to a deeper structure, a vast, infinite field of creation still unfolding in silence. The notion of a multiverse blurs the line between physics and philosophy, between science and speculation. It forces humanity to confront a deeper question. If other universes exist, what does that mean for meaning itself? If reality is infinite, if every possible configuration of matter and energy is realized somewhere, then the uniqueness of this world, this life, even this thought, dissolves into the boundless. Some find that thought liberating, others deeply unsettling. But perhaps the multiverse, rather than diminishing our significance, amplifies it. For in a cosmos of infinite possibility, consciousness itself becomes a rare bloom, a flicker of awareness within a storm of endless creation. And that awareness, that ability to wonder, to measure, to dream, binds the observer to the observed, the universe to the mind that reflects it. As telescopes like James Webb peer deeper into time, they edge ever closer to the frontier where inflation began, the threshold between the visible and the unknowable. Each new observation tightens the constraints, shaping the models, refining the possible. But still, the question lingers in the darkness. Was the Big Bang truly the beginning, or merely one spark among an infinity of fires, each igniting its own universe, each vanishing into eternity? In the equations of physics, there is room for such grandeur. Inflation, quantum mechanics, and general relativity all suggest that creation is not a singular event, but a process, continuous, recursive, and eternal. Perhaps universes are born the way stars are, collapsing, igniting, and expanding one after another across the boundless sea of being. And if that is true, then the cosmos we call home is but one verse in an endless poem, written not in ink, but in energy, time, and space. Yet for all its beauty, the multiverse remains an idea perched at the edge of science, a hypothesis without proof, a mirror held up to human imagination. Some physicists embrace it as a natural consequence of inflation, a necessary expansion of cosmology. Others warn that it may mark the limit of testable science, a step from explanation into metaphysics. The debate is fierce and profound. For to accept the multiverse is to accept that the universe may never offer a final answer, that truth itself may be relative to the bubble one inhabits. It means surrendering the dream of a single, complete theory, and instead embracing the possibility of infinite variation, infinite creation, infinite truth. Perhaps that is what the cosmos has been telling us all along. That reality is not singular, but plural. That existence is not an island, but an ocean. And that within this ocean, every act of observation, every flicker of consciousness is itself a ripple in the infinite. In the end, the multiverse is not a claim of certainty. It is a gesture toward the unknown, a reminder that even as science extends its reach across light years and epochs, the greatest mystery may still lie just beyond the boundary of our own horizon, beyond the galaxies, beyond the last photons of the cosmic dawn, beyond the curve of space-time itself. The universe may continue. Not as an ending, but as a beginning repeated endlessly, each bubble expanding into silence, each reality unfolding its own story. And somewhere in one of those universes, a species rises, looks to the night sky, and wonders if it is alone. Chapter 9. Quantum Veils. Reality beneath space-time. In the vast stillness between galaxies, space seems empty, a silent canvas stretched across eternity. But beneath that stillness, beneath the smooth geometry of space-time, lies a storm so violent, so restless, that even the word nothing loses its meaning. At the smallest scales known to physics, far below atoms, far below quarks, the universe is not calm. It trembles, it flickers, it boils with invisible motion. This is the quantum vacuum, the foundation upon which reality itself is built. What appears to be emptiness is, in truth, a restless sea of creation and annihilation. Particles burst into existence, then vanish again, in time so short they cannot be measured. Physicists call this the zero-point energy, the lowest possible energy that the universe can possess. It is the hum of existence itself, the background whisper of reality. Even in perfect emptiness, energy remains. Even in silence, the cosmos sings. Quantum mechanics shattered the ancient dream of a continuous, predictable universe. What once seemed smooth and absolute, space, time, cause and effect, now dissolve into uncertainty. At the Planck scale, where distances shrink to 10 to 35 meters, space-time itself begins to fracture. Geometry becomes granular. Time loses its steady rhythm. The very stage upon which the universe unfolds begins to blur. Physicists call this domain the quantum foam, a realm of violent fluctuations where the fabric of reality seethes like boiling water. Tiny wormholes open and close. Miniature black holes flicker in and out of being. The laws of geometry themselves are rewritten every instant. To peer into this domain is to look into the raw machinery of creation, the place where space and time may not even exist, but are born as emergent illusions. A growing idea in modern physics suggests that space-time itself may not be fundamental. Instead, it might emerge from something deeper, something woven not from distance or duration, but from information. This idea arises from the most mysterious of all quantum phenomena, entanglement. When two particles become entangled, their properties link instantaneously, no matter how far apart they are. Measure one, and the other responds, even if it lies on the opposite side of the universe. To Einstein, it was spooky action at a distance. To quantum physicists, it is the most essential feature of reality. Entanglement is not just a connection within space-time. It may be the very process that creates spacetime. Theoretical physicist Juan Maldacena's groundbreaking ADS-CFT correspondence revealed a strange duality. A universe with gravity, existing in 3 dimensions, can be mathematically equivalent to a universe without gravity living on its 2-dimensional boundary. In other words, everything within a volume of space might be fully described by information encoded on its surface, like a hologram. This concept, known as the holographic principle, suggests that the cosmos we experience, with its depth, stars, and galaxies, might be a projection of deeper quantum information written on the edges of reality itself. The seeds of this idea sprouted from black holes, the most enigmatic structures in the universe. According to Einstein's general relativity, a black hole's gravity crushes matter into an infinitely dense singularity, hidden behind an event horizon from which not even light can escape. But quantum theory refuses to be silent. In 1974, Stephen Hawking discovered that black holes are not entirely black. Through quantum fluctuations near the event horizon, they emit faint radiation, particles born from the quantum vacuum itself. This glow, known as Hawking radiation, means black holes slowly evaporate, losing mass until they vanish into nothingness. But if they vanish, what happens to the information they once contained? According to quantum mechanics, information can never be destroyed. Yet, if a black hole evaporates completely, the data describing everything it consumed seems to disappear forever. This is the black hole information paradox, a riddle that shakes the foundations of both quantum theory and relativity. Over decades, physicists like Leonard Susskind, Gerard 't Hooft, and Maldacena have wrestled with this puzzle, and from that struggle emerged a revelation. Perhaps the information is not lost at all, but stored on the surface of the black hole itself, encoded in the quantum entanglement between particles. In this view, the event horizon becomes a cosmic hard drive, a 2-dimensional sheet holding the data of everything that falls within. The black hole, in its depthless darkness, becomes a hologram, the ultimate projector of hidden information. And if that principle applies not just to black holes, but to the entire universe, then everything, every star, every atom, every heartbeat, could be the shadow of deeper quantum entanglement across the cosmic boundary. Reality then would not be built of matter or energy, but of relationships. The structure of space-time would arise from the pattern of how things are entangled, how information connects across the quantum web. We are not merely in space-time, we are woven from it. The more scientists peer into this web, the stranger the universe becomes. Quantum field theory tells us that every point in space is alive with vibration, infinite modes of energy dancing at every frequency. Yet when we try to calculate the vacuum energy that this implies, the result is catastrophic. 1 to 120 times larger than the energy density we actually observe. That impossible number, known as the cosmological constant problem, remains one of the most staggering mismatches in physics. It means that something, somewhere, is missing from our understanding. That perhaps what we call vacuum energy is not truly energy at all, but a misreading of a deeper structure beneath space-time. Some physicists propose that zero-point fluctuations might cancel out through unknown symmetries. Others suggest that the vacuum energy is dynamically adjusted by feedback with cosmic expansion. And still others whisper that space-time itself might emerge only as an approximation. That below a certain threshold, the notion of energy, distance, or even space dissolves entirely. If so, the vacuum, the emptiest thing imaginable, might not be nothing. It might be everything. In recent years, the boundary between gravity and quantum mechanics has begun to blur in new ways. Through quantum gravity research, in string theory, loop quantum gravity, and beyond, scientists are searching for the blueprint that unites these two great pillars of physics. Some models imagine space-time as a vast interconnected network, a spin foam of quantum links that weave together to form geometry itself. Others describe reality as a tensor network, where each connection encodes quantum correlations that, when viewed collectively, give rise to the illusion of smooth space. In both visions, the universe resembles not a stage upon which events unfold, but a living computation, a ceaseless unfolding of information. It is as though reality itself is a quantum algorithm, running not in space-time, but creating it. And then there is the ultimate speculation, a thought so daring it treads the edge of philosophy and physics alike. If our universe is a hologram, then everything we perceive, matter, light, time, consciousness, could be the projection of a deeper, unseen reality. Like images cast upon a screen, our entire cosmos might be a shadow of something beyond it. This is not the claim of fiction, but the mathematical consequence of our best theories of black holes and quantum fields. Some researchers, like those behind the Fermilab holometer, have even attempted to detect tiny vibrations, potential signatures of holographic noise, the faint jitter of the cosmic projector itself. The results remain inconclusive. The veil, for now, remains intact. But even if the holographic nature of the universe is never proven, it carries a profound philosophical resonance. It suggests that reality is not built upon solidity, but upon connection. That every atom is entangled with the whole. Every fluctuation echoes through the infinite web. The cosmos, in this view, is not a machine. It is a mind, a structure of information, awareness, and order emerging from the quantum sea. And if space-time itself can emerge from entanglement, then perhaps consciousness too is not a separate phenomenon, but another expression of the same universal code. The universe perceiving itself through the eyes it created. At the threshold of understanding, physics begins to resemble poetry. Equations give way to metaphors, and the search for truth becomes a meditation on existence itself. Reality, once thought to be built from matter and energy, now seems composed of patterns, probabilities, and information. Each discovery reveals not solidity but subtlety, not answers but deeper mysteries. Beneath the visible world, beneath the stars and the galaxies, beneath even space and time lies a realm without form, where creation and destruction are the same breath, where the laws of nature themselves are born and reborn in endless quantum motion. At that depth, reality ceases to be a place. It becomes a process, a continuous unfolding of information, weaving itself into the tapestry of being. Space, time, gravity, light, all emerge as shadows from this deeper dance. And perhaps what we call the universe is not the final layer of truth, but only the first surface of something infinitely more profound. In the darkness between the stars, space-time stretches silently, vast, smooth, eternal. But beneath that silence lies the hum of the quantum, the pulse of creation, an unseen rhythm, endless, intricate, eternal. It is here, beneath the veils of reality, that the universe whispers its deepest secret. That everything, galaxies, black holes, atoms, and thought, is not made of space and time, but born from it. And beyond that birth, perhaps, lies something even greater, a truth not of distance or duration, but of meaning itself. Chapter 10. The fate of everything. The end of the universe. In the beginning, there was light. a searing brilliance that flooded the newborn cosmos, carrying the echoes of creation into infinite darkness. 13.8 billion years later, that light still travels, stretched, dimmed, but unbroken, a whisper from the dawn of time. Yet every journey, no matter how vast, moves toward an ending. The universe, too, is not eternal in the way ancient minds once dreamed. It is a story with chapters, and somewhere beyond imagination, its final page awaits. The cosmic timeline is a vast and intricate chronicle. It begins with the Big Bang, the sudden birth of space and time from a point smaller than an atom. For billions of years, matter coalesced, stars ignited, galaxies spun into spirals of light. From chaos, structure emerged, and within that structure, the seeds of life. But as the cosmos aged, its rhythm began to slow. The brilliant fireworks of stellar creation waned. The universe, once blazing with heat and motion, began its long and quiet transformation, from fire to frost. Today, astronomers stand upon this middle ground, watching the heavens expand and cool. Galaxies recede, light stretches. Time itself accelerates under the invisible hand of dark energy, the mysterious force pushing the fabric of space apart. If this expansion continues unchecked, the stars that now shimmer above will someday fade beyond sight. The Milky Way will become an island in an ever-growing ocean of darkness, and the universe, once alive with brilliance, will drift into a silence deeper than any before. To glimpse the end is to confront the deepest question in cosmology. How will it all end? Physicists have proposed several possible destinies, each drawn from the delicate balance between gravity, matter, and dark energy, each one a different kind of eternity. In one vision, gravity wins. If the density of the universe were high enough, its expansion could someday slow, stop, and reverse. Galaxies would begin to draw together. Stars, once separating, would move inward again. The cosmos would contract, collapsing back into the singularity from which it came. This is the Big Crunch, a universe that ends as it began, in fire, a mirror to the Big Bang, a cosmic heartbeat of creation and destruction. In such a scenario, time would loop upon itself. Matter and energy would be crushed into infinite density, perhaps triggering another expansion. A new universe born from the ashes of the old, an eternal cycle of birth, death, and rebirth, a phoenix-like cosmos, forever consuming and recreating itself. Yet the evidence no longer favors this fiery end. The expansion is not slowing, it is accelerating. And that acceleration means gravity has lost the cosmic tug-of-war. The second possibility is far more chilling and far more likely. If dark energy remains constant, the expansion will continue to speed up forever. Galaxies will slip away from one another, their light redshifted beyond visibility. The cosmic web, once vibrant with clusters and filaments, will stretch into nothingness. Over the next 100 billion years, the stars of the Milky Way will exhaust their fuel, collapsing into white dwarfs, neutron stars, and black holes. The night sky, once bright with billions of suns, will fade to black. This is the path toward the Big Freeze, or the heat death of the universe. In this future, the cosmos does not explode nor collapse, it simply fades. The temperature everywhere will approach absolute zero. Motion will cease. Entropy, the measure of disorder, will reach its maximum. Every process that sustains structure, from nuclear fusion to chemical reaction, will end. Even time itself, tied to change, will lose meaning. The universe will become a shadow, a thin, cold fog of elementary particles drifting through infinite darkness. It will no longer become, it will simply be. But there exists a third, more violent ending, one driven not by stillness, but by unstoppable acceleration. If dark energy is not constant, if it grows stronger with time, then the universe will not merely expand. It will tear itself apart. Galaxies will fragment. Solar systems will unravel. Planets will be ripped from their orbits. Even atoms will be shredded as space itself expands faster than light can keep up. This is the Big Rip, a cosmic apocalypse. In this unimaginable finale, the fabric of space-time becomes unstable, disintegrating under its own expansion. All bonds, gravitational, atomic, and quantum, are destroyed. And at last, even the smallest particles dissolve into the void. Everything that ever existed, from stars to souls, will be erased in a single endless instant. Each of these endings depends upon the behavior of dark energy, the most mysterious element of existence. It makes up nearly 70% of the universe, yet no one knows what it is. It may be a property of space-time itself, Einstein's long-doubted cosmological constant, or it may be something dynamic, evolving, shifting, changing as the cosmos ages. Some theories suggest dark energy might one day reverse its sign, pulling everything inward. Others imagine it decaying, leaving behind a cold but stable universe. And some whisper that it may grow without bound, dragging all of creation toward oblivion. Dark energy is not just an ingredient of the universe, it is the architect of its fate. In the far future, long after the last stars have burned out, the universe will enter what physicists call the degenerate era. Black holes will dominate the cosmic landscape, silent, invisible, and ancient. Over unimaginable stretches of time, even they will begin to evaporate through Hawking radiation. A black hole the mass of the Sun will vanish in 1067 years. The largest supermassive black holes, weighing billions of suns, will take up to 2100 years to evaporate completely. When the last of them fades, the universe will be left with nothing but stray photons, neutrinos, and the faint residue of space itself. Entropy will reign supreme. This final age, the Dark Era, will stretch on for eternity. No light, no warmth, no memory, only the slow, endless drift of the last particles in an ever-expanding void. For those who ponder such futures, the emotion is neither fear nor despair, but awe. For this end is not a failure, it is the natural consequence of time itself. Entropy is not destruction, it is evolution. From the first explosion to the final silence, the universe moves inevitably from order to freedom, from structure to possibility. In that endless expansion, perhaps meaning itself becomes unbound. And yet, even here, in this vision of cosmic death, there are whispers of something beyond. Some physicists imagine that the decay of one universe might trigger the birth of another, that quantum fluctuations in the dying dark could ignite new big bangs, scattering seeds of creation across the multiverse. Others speculate that information, the quantum blueprint of everything that ever was, cannot be destroyed, but must find new form, perhaps embedded within the fabric of the next reality. In such visions, the end of the universe is not an extinction, but a transformation, the final act in an infinite cycle of renewal, a cosmic breath, expansion, contraction, rebirth. But these remain speculations, dreams at the edge of physics. The only certainty is that the universe will change, and in that change, it will lose everything we know. If one could stand at the end of time, gazing into the frozen horizon of eternity, there would be nothing to see. No galaxies, no stars, no color, no sound, just the faint whisper of ancient light. Photons stretched beyond imagination, flickering through infinite emptiness. This is the final image of the cosmos. A darkness so complete, it becomes pure. A silence so deep, it seems to echo. And yet, even there, in the cold ashes of eternity, the story of everything remains written into the structure of space-time. Every atom that ever existed, every heartbeat, every thought, recorded in the ripples of energy that once were. The universe may die, but its memory will not vanish. It will dissolve, diffused, scattered, but eternal in its traces. The cosmos began not from nothing, but from potential, from a state so unstable that existence itself was inevitable, and perhaps at its end, it will return to that same fertile nothingness. A perfect equilibrium where time ceases to flow, and yet the possibility of rebirth remains. In the quiet of that final night, when the last particle fades into darkness, the universe will have fulfilled its journey, from chaos to order, from order to stillness. It will have lived every possible story, sung every possible note, and in that silence, that deep, eternal silence, lies something profoundly beautiful. For the end of the universe is not the end of wonder. It is the completion of the greatest poem ever written, a poem of light, of time, of being. Its verses began in fire. They end in shadow. But between those two infinities, existence itself was born. And for a moment, the cosmos knew itself. Chapter 11. The Tools of the Future. humanity's quest to understand in the long twilight of human knowledge, where the horizon of understanding stretches into the infinite, a new generation of instruments prepares to awaken. They are not built of mere metal and glass, but of vision, perseverance, and the unrelenting desire to comprehend the cosmos itself. The Nancy Grace Roman Space Telescope, often called Hubble's Air, will soon open its eye to the deep sky. Its gaze will sweep across vast regions of space, capturing the faint signatures of dark energy, the invisible force accelerating the expansion of the universe. With a field of view hundreds of times larger than Hubble's, Roman will not just glimpse the universe, it will map its architecture, tracing the delicate scaffolding of cosmic evolution. Each image a time capsule of creation, each photon a whisper from billions of years ago. Beyond the reach of visible light, another machine listens, not to what can be seen, but to what can be felt. LISA, the Laser Interferometer Space Antenna, will drift silently through the void. 3 satellites separated by millions of kilometers, connected by beams of pure laser light. Together, they will sense ripples in space-time itself, gravitational waves, the faint tremors of colliding black holes and merging galaxies. These waves will speak of cataclysms that shook the universe before Earth was born, of dances between invisible giants whose rhythms still echo through existence. And on Earth, beneath mountains and in deep caverns, the search continues. Next-generation particle colliders, successors to CERN's mighty Large Hadron Collider, are being conceived to unravel what lies beyond the standard model. They will probe energies never before reached, searching for hidden dimensions, dark matter particles, and the fingerprints of a deeper symmetry buried beneath quantum chaos. Yet even as machines grow more powerful, the universe resists simplicity. To understand its vastness, scientists now recreate the cosmos itself within supercomputers. Inside these digital universes, billions of galaxies emerge from equations. Dark matter filaments form like veins of shadow. Gas clouds condense, ignite, and die. Every simulation is a mirror, an echo of creation played back in accelerated time. These virtual cosmoses reveal what cannot yet be seen, offering predictions, puzzles, and new questions to pursue across the real sky. But now, a new kind of observer joins the quest: artificial intelligence. Trained on the deep archives of telescopes and satellites, AI systems begin to detect patterns too subtle for human minds. They trace the invisible threads linking galaxies, predict the hidden structures of dark matter, and classify the faintest glimmers of distant stars. In their computations, the universe begins to speak its own language, a syntax of energy and probability, decoded not by intuition but by learning. Still, behind all machines, behind every lens, sensor, and algorithm, there remains one enduring force: human curiosity. It is older than the stars we study. It has survived every age of darkness, every cosmic silence. It is what drives the hand that builds telescopes, the mind that writes equations, and the heart that dares to ask why. As we stand at the edge of knowledge, surrounded by tools that can see to the dawn of time, we are reminded of something humbling: that no machine, however perfect, can replace wonder. For it is wonder that compels humanity to reach again and again into the void, not to conquer it, but to listen. The quest to understand is endless. It is the quiet flame that will outlast empires and eras, burning still even as the last star fades and the universe grows silent. For as long as there are minds that can imagine, the cosmos will never truly be dark. Chapter 12. The universe, looking at itself in the stillness between galaxies, where light drifts across eons and silence reigns absolute. Something extraordinary has occurred. The universe has become aware of itself. Out of the cold dust of ancient stars, atoms have learned to think. Carbon, oxygen, and hydrogen, once the raw material of nebulae, now dream, question, and seek to understand. It is a quiet miracle, written not in divine decree, but in the patient language of evolution and time. This is the paradox of consciousness, matter that gazes back upon the cosmos that made it. From the chaos of quantum fields and nuclear furnaces, there emerged minds capable of reflection. Within their neural storms flicker the same forces that govern galaxies: electricity and gravity, order and entropy, pattern and decay. Each thought, each question, is a tiny echo of creation itself. Carl Sagan once said, We are a way for the cosmos to know itself. And in that phrase lies one of the deepest truths of existence. Through human eyes, the universe observes its own beauty. Through curiosity, it retraces its own beginning. Every telescope turned to the stars, every equation etched onto a page, is the cosmos awakening to its own nature, a grand act of self-realization. But in this realization also lies mystery. Why does existence allow for awareness at all? Why should a collection of lifeless particles give rise to wonder, love, and meaning? Physics can describe the firing of neurons, but not the quiet awe of watching the night sky. Biology can trace evolution's path, yet cannot explain why beauty stirs the human soul. Between these truths lies a gap. The bridge between science and spirit, between knowledge and wisdom. Science, in all its triumphs, remains humble before this enigma. Every discovery widens the horizon of ignorance. Every solved mystery reveals deeper questions waiting beneath. The farther humanity reaches, the more it realizes how fragile and fleeting its understanding truly is. Perhaps that humility is itself a form of wisdom, an acknowledgement that knowing is never complete, that the act of seeking may be the purpose of consciousness itself. The universe speaks not in words, but in silence, in the faint hiss of cosmic microwave background radiation, in the slow drift of galaxies receding beyond view. Its messages are written in light, gravity, and probability, and perhaps within that silence lies something intentional. Not a plan, but a reflection. For every question humanity asks, the cosmos answers with a deeper mystery, as if reminding its observers, "You are not separate from me. You are part of the story you seek to understand." There is a poetic irony at the heart of existence. In mapping the stars, humankind discovers not the boundaries of space, but the contours of its own mind. In tracing the birth of galaxies, it confronts its own fragility and impermanence. The same forces that sculpt cosmic filaments shape the neurons within the human brain. The universe is not out there. It is within, mirrored in consciousness, echoed in thought, alive in curiosity. As stars age and fade, and as the universe drifts toward entropy's quiet end, this brief spark of awareness may vanish. Yet, for this fleeting cosmic moment, the universe knows itself. Through the eyes of a single species on a small blue world, the cosmos contemplates its own beginning, and perhaps its fate. Maybe this is its purpose. Not endless expansion, not the forging of stars or the birth of galaxies, but simply to be seen, to be known, to feel its own beauty reflected in the fragile minds of those who dare to wonder. And when all lights fade, when the last photons dissolve into darkness, that wonder will have mattered, for in the quiet of eternity, the memory will remain, that once the universe looked at itself and saw that it was beautiful. Chapter 13. The eternal question, what lies beyond the horizon? The edge of all that can be seen, there exists a line, faint, unreachable, and yet profoundly real. It is the cosmic horizon. Beyond it, the light from distant galaxies has not yet arrived, its journey stretched thin by the universe's relentless expansion. It is the ultimate boundary of observation, not a wall, but a veil woven from the limits of time itself. Every telescope, every equation, every dream of exploration meets this invisible border. Beyond it, the map of existence fades into uncertainty. What lies there? More galaxies, more universes, or perhaps something entirely different? The laws of physics, so certain within our cosmic bubble, dissolve into speculation at this frontier. The observable universe, a sphere 93 billion light-years across, is but a small island in a sea without end. Astronomers know that there is more beyond, perhaps infinitely more. Galaxies so distant that their light will never touch us. Realms that exist forever outside the reach of causality. It is not emptiness that lies beyond, but mystery, a continuation of creation's silent rhythm, hidden behind the horizon of our understanding. In that sense, the universe mirrors itself. Every beginning echoes an ending. The Big Bang, the eruption of all things, may not be a singular event, but part of a greater cosmic symmetry, a pulse in an eternal cycle of birth and decay. Some physicists imagine universes budding off from others, like foam upon an infinite ocean. Others suggest the cosmos might one day fold in on itself, collapsing the very fabric it once unfurled. Time, space, and matter These are not absolutes, but fleeting expressions of something deeper. And as the horizon recedes, as it always will, it leaves behind a haunting realization. Perhaps the universe was never meant to be fully known. Perhaps knowledge itself is just one way the cosmos experiences its own mystery. Einstein once wrote, "The most beautiful experience we can have is the mysterious." In those few words lies the quiet essence of science. Not conquest, but reverence. Not certainty, but wonder. For to stand beneath the night sky is to confront both immensity and intimacy. To sense that the stars, though distant, are part of a single unfolding story. At the frontier of that story, the universe whispers through radiation older than galaxies, the cosmic microwave background, a soft hiss echoing from the first light of creation. It is the voice of time itself, faint but eternal, carrying across an ocean of darkness. In the final moments of cosmic reflection, one truth endures. The horizon is not an end, but an invitation. To question, to dream, to feel. The farther humanity peers, the more the universe reveals not answers, but emotions, awe, humility, longing. As the camera drifts outward, past the Milky Way, past the clustering filaments of the cosmic web, the stars begin to fade. Galaxies blur into mist, and the universe folds into a silent shimmer of light. And in that fading light, a single thought lingers. Perhaps the universe was never meant to be solved, only felt. The image dissolves into darkness. The hum of cosmic radiation whispers one last time. The sound of the beginning, echoing endlessly toward what lies beyond. Fade to black.